shown in the figure below is a mass pressed against a spring. The spring is compressed by 0.1 meters. When released, the mass will be shot across the surface. A. Calculate the velocity of the block at position 2, which is located here. And B. Calculate the velocity of the block at position 3, which is located there. The first thing to do in any problem is to decide what kind of methods you wish to use to solve that problem. F equals ma methods sum forces and set them equal to mass times acceleration at one instant in time. These methods become extraordinarily difficult in a problem where the force varies. Here, the problem begins with a mass on the spring. Later, the mass is away from the spring, following which it will climb an inclined plane and then go across another smooth surface. For that reason, force methods are not a good approach to solve this problem. Instead, what we want to use are energy methods, and let's briefly review the manner by which we solve energy problems. The equation for energy tells us that the work due to all non-conservative forces is equal to the change in total energy of some system of objects. Now, this kind of a law, which is very similar to the momentum law, has a particular style by which we apply it, and that style has effectively two branches, depending upon what you have for your non-conservative work. When there isn't any non-conservative work, so work non-conservative is equal to 0, remember that friction is sort of the prototypical non-conservative source of work. If in an absence of friction and other non-conservative forces, we will decide to solve our problem by setting the total energy at some moment, let's say we called that moment 1, equal to the total energy at another moment, yielding us an equation with presumably only one unknown, because you only get one equation since energy is a scalar. On the other hand, for those problems in which there is work due to a non-conservative force, work non-conservative isn't 0, in that case we simply have to solve the formula as given. We need to write an expression for the non-conservative work. If it's friction, the non-conservative work is usually negative, but not always, and then set this equal to the change in total energy. Change in is always, as we remember, after minus before, so in this case we'll set it as moment 2 minus the total energy at moment 1. Clearly, this process of formulating the equation is driven by a single task that you need to accomplish at the beginning of the problem, and that is define your moments. In the problem at hand, these moments have almost been defined for us. We're given a description of what it is like when the mass is pressed against the block, still motionless, and that will be our moment 1. We are then asked what are the conditions when the block is sliding across the surface, indicated by moment 2. And finally, we're asked what is the velocity at position 3, or in other words, moment 3. So what we will need to be doing is connecting the moments through the appropriate energy law. In this particular problem, since there is no mention of friction, we will assume that all surfaces are frictionless, and therefore our solution will be of the form in which we conserve energy. Since our moments are nicely defined, we decide to connect moment 1 to moment 2, and the principle by which we connect the two moments is conservation of energy. Since there is no work due to a non-conservative force, we'll be connecting the total energy at moment 1 to the total energy at moment 2. The recipe that we follow in formulating a conservation of energy solution is then to list all of the energies at each location. And I like to be really explicit. I like to put in a term of 0 even for those energies that aren't present at a particular moment. So let's focus for a moment at moment 1. At this stage in the course, you typically know of 3 types of energy: kinetic energy, potential energy due to a spring, and potential energy due to gravity. We'll ask about each one of these at moment 1. So, at moment 1, do we have kinetic energy? The answer is no, because it's stationary, and so I'm going to write a 0 representing the kinetic energy. At moment 1, do we have gravitational potential energy? Well, gravitational potential energy goes by the formula mgy, and in getting from moment 1 to moment 2, since we're using the same height, let's define y equals 0 just where we are, and so at moment 1 we also don't have any gravitational potential energy. Finally, the third question for moment 1, do we have spring potential energy? The answer is absolutely yes, we do. And the amount of the spring potential energy is 1/2 times the spring constant times the compression of the spring at moment 1 squared. Halfway there. All we need to do to complete the formulation of this problem is write an expression for the total energy at moment 2. We have the same 3 questions to ask ourselves. At moment 2, do we have kinetic energy? This time the answer is yes, because we know the object will be moving at moment 2, and so we will write the amount as 1/2 mv squared, and just to be good with our notation, we're going to call this v2 so that we specify the velocity is at moment 2. We ask ourselves the question at moment 2, do we have gravitational potential energy? The answer is no. And at moment 2, do we have spring potential energy? Moment 2 is presumably so far from the original spring that the mass has lost contact with the spring, and so there is no longer any energy due to a compressed spring. This is our equation, and hopefully it only has one unknown. Well, what do we know? We know that the spring constant itself is 100. X, the compression, is 0.1, which we're going to need to square. The mass is 2 kilograms. And then velocity 2 squared. The only unknown in that equation is velocity 2, which we can solve for rather easily. Each time we multiply 100 by 0.1, it drops by 1 decimal place. So 100 times 0.1 squared is simply 1. The left-hand side becomes 1/2. On the right-hand side, the 2's will cancel, leaving us with a 1. And so velocity at moment 2 is equal to the square root of 1/2, which is 0.707 meters per second. Now let's take a look at the second question. What is the velocity at moment 3? Going back to our original diagram, we notice that moment 3 is located at the top of the hill over here. And we're going to need to solve for information at moment 3. Now what we know is that energy is conserved all the way from moment 1 through moment 2 to moment 3. Therefore, the total amount of energy at all 3 of these moments is exactly the same. So to solve for what's going on at moment 3, we can either connect the energy at moment 1 to moment 3, or we can connect the energy at moment 2 to moment 3. I'm going to choose to connect moment 1 to moment 3, and here's the reason. Although I'm fairly confident that our calculation for V2 at moment 2 was correct, if you were in the middle of an exam and you weren't thoroughly certain that your answer to part A was correct, it is safer to use the initial information at moment 1 to connect to moment 3 and thereby not risk the chance that any mistake you've made in part A is transferred into a mistake in part B. So here we go. Remember, looking at the figure, that moment 3 is on top of a hill of 0.02 meters, and the object is most likely still moving because that's a rather short hill. connecting moment 1 to moment 3. We're going to be using the principle of conservation of energy because the work due to non-conservative forces between moment 1 and 3 is equal to 0. Therefore, the technique or recipe by which we build our energy equation is to set the total energy at moment 1 equal to the total at moment 3 thereby resulting in a single equation. This single equation should have one unknown. When we solve for that unknown, we've completed the problem. The total energy at moment 1 is exactly the same as in the previous part. Moment 1 does not have kinetic energy because the object is not yet moving. Moment 1 we're going to be defining as the y equals 0 location. But moment 1 definitely has spring potential energy, 1/2 k times the x at moment 1 squared. Looking at moment 3, I believe that we do have kinetic energy. That's 1/2 m times velocity at moment 3 squared. At moment 3, we also have gravitational potential energy because we're up on a hill. That's going to be mg times the height at moment 3, or I like to call it the y position at moment 3, plus spring potential energy. Well, not at moment 3. We're now too far from the spring. So this equation indeed has only one unknown. The only unknown in this equation is V3, and we can fill in the rest of the numbers. 1/2, 100 for the spring constant, 0.1 for x at moment 1, equals 1/2. The mass is 2, velocity 3 squared, plus a mass of 2 kilograms, g is 9.8, and we've been told that the height of the hill is 0.02 meters. Again, the 2's will cancel in the kinetic energy term. And if we move the gravitational potential energy term over to the left-hand side of the equation, we'll be left with an expression with only V3 squared on the right-hand side. On the left, we'll have the result from the spring potential energy minus the result from the gravitational potential energy, which is twice 9.8 times 0.02. And this leads us to the answer that V3 is equal to 0.329 meters per second. So the style of all energy problems is, number 1, identify the moments. Number 2, decide whether you will be dealing with a non-conservative force or not. And then number 3, count the energies at each moment and make sure you set 0 for the terms that aren't energy at each moment and the appropriate expression for what is an energy. Good luck with your energy problems.